Good afternoon. This is David Eastwood, Geotech Engineering and Testing. How y'all doing? Thanks for taking the time to go over this webinar with me. It's an interesting project we worked on, and I thought it'd be a good training program. Hope everybody can hear me. Um, let's see if we got any chat in here. Yeah. So we got one thing here, one comment so far. So if you have any questions, ask me in the Q&A deal. Audience makeup, lots of engineers, a lot of structural guys and forensic guys. We've got about 160 people, a lot of forensic and structural guys here. If you need to reach me, my email is de@geotecheng.com. My number is 713-699-4000. This is going to go on YouTube. You can watch this program on YouTube. Geotech engineering and testing has been around for 39 years. Man, I'm getting old. We do geotechnical, environmental materials, and geoforensic engineering. We got 60 people, engineers, geologists, technicians. We work all over Texas, Louisiana, Oklahoma, New Mexico, and Arizona. And we have all rigs, and we can move on projects quickly. If you have questions, again, type it into the Q&A section or chat. Um, project site, South Texas. It's an addition to a middle school. Project timeline. Basically, the agenda is the project timeline, site visit, field exploration, laboratory tests, engineering analysis, reasons for distress, repair techniques, recommended additional studies. Timeline. They did the initial geotech report in 2008, which was wrong, the geotech report. They did a civil report January of 2009, and all the drawings were done in 2009. And the finished addition to this project towards the end of 2009. We were engaged in 2024, December, because the client was saying that there was a lot of problems on this building, a lot of cracks, movements, and we did a site visit in December of 2024. That was New Year's Eve, by the way. And in 2025, we did a bunch of testing and a report. Site visit. This is the observation points of the first floor of it's a two-story structure. These red points are within the school where all the cracks and stuff were occurring. That's first floor, and that's the second floor. Shows all the red points where a lot of the cracks and movements are occurring. So observations of the exterior of the building. This is the building. This is a brick veneer structure. The joint spacing in the brick is about 30 feet here. And so let's see. Anyway, the brick joint for a typical building like this should be about 20 feet, not 30 feet. You go look at the building itself. Some of the sidewalks have heaved up. We got negative drainage towards the building. And of course, the gutters are dumping water right on top of the sidewalks. And this whole area was wet. There was this big tree, not big tree, this little tree out here, not too far from the building. It really doesn't affect it right now. It's about 25 feet tall and 21 feet away. But once it gets this oak tree get bigger, of course, it's going to have foundation problem with the building. See, if you go outside the building and start looking at it, you see these cracks in the brick, and the more cracks in the brick. This is the other side of the building. Brick joint here is about 20 feet, which is fine. They removed this window, kind of like a frame deal around the building, windows, because of the movement, it got loose and fell down. So they didn't want it. You know, if you look at the previous pictures, uh, these window stuff, all of them have been taken out, the window frames. Because of the movement, they were afraid that this window frame was going to fall on the kids, so they removed it. So here's typical cracks out the exterior of the building. In the brick, the window frame was removed. Here's another one, window frame removed. Inside was pretty bad. You could see between column, CMU block joints, a lot of movement. The columns are moving. Columns are supported on drill piers. A lot of separation, 0.1 inch separations. A lot of sheetrock cracks, CMU block cracks. More CMU cracks. Stair steps cracks through the CMU. Separations again between the column, CMU block, CMU cracks. Again, you can see more separations here. More cracks here. More cracks here. We kind of checked the plumbness of the walls. The walls, for the most part, they were pretty vertical. There was some deflection, not very much. Again, we see the cracks. We check the plumbness. More separations between the columns and the CMU blocks. See cracks right there. Again, here, cracks in the CMU block corner area. See the stair step cracks. Separations between the columns and CMU walls. More cracks here in the CMU. See the crack in here. Here again, you can see the separations. More cracks. I mean, this was throughout the whole building, first floor and the second floor. Foundation system consisted of drill piers. Bunch of drill piers in here. Basically, the design was the drill pier with the concrete strength of 2,500 psi at 28 days. The geotech said put the piers 13 feet deep. And here we have really fat clay, really hard fat clay all the way down. And of course, this is South Texas, really dry. Underreams here, 1636, 1850, 18 diameter shaft, 50 diameter bell. Some of them are 24-inch shaft, 60-inch diameter bell. Some of them are 30-inch diameter shaft, 78-inch bell at a depth of 13 feet below finished floor. Okay? Below finished floor. The floor slabs, they had 8-inch void boxes under the floor slabs and in the grade beams, which was good. Field exploration, we did ground penetrating radar, GPR, concrete core drilling and sampling, installed some piezometers to measure where the water is. We did macro elevations. We did drill footing exposure. We did test pits for the piers and the grade beams. So here kind of shows what we did here. These are the boring B4, boring B2, boring B1, piezometer number 1, piezometer number 2, test pits 1, test pit 3, test pit 2, test pit 4. So we did 4 corings of concrete floor slabs. We did 4 borings inside and 3 borings outside. So we did GPR at 7 locations where we cored the concrete. These are the borings outside to a depth of 30 feet. The borings inside, we try to get 20 feet. But these are 30-foot borings outside in the parking lot. They were covered with concrete. And then we had test pit excavations, 2 locations with drill piers and 2 locations for grade beams. GPR, of course, as you know, it's basically uses an antenna that transmits electromagnetic energy similar to what cell phones are. It's got a receiver within it, and it basically receives a reflected signal that it sends out, and when it encounters soils with 2 different dielectric properties. GPR was conducted at 7 locations in the floor slab areas to basically perform a standard borehole clearing. It looks like a lawnmower. You just running in there, run it on the floor slabs. We did it inside and outside. Here's the GPR doing it inside, kind of locating where the steel is. This is the hand device. We locate the borings where we don't have to go through the steel, possible conduit. Of course, we didn't want to hit the stuff on the bottom. And so we locate the boring locations. And again, let's see the rebars in here, conduit. Here's another location. This is the boring location. These are the rebars. Recommended coring location. Here's another location. The rebars are over here, so we did it kind of like where there's no rebar, we did the borings. We also did it in the parking lot. Location of the cores where rebars are around it. Here's another location. Or 7 locations, 4 inside, 3 outside, 7 locations total. 4 boring locations inside and 3 boring locations outside. Here's another location. This is where the steel was. This is the boring location. Concrete coring, we cored inside and outside with the concrete coring device. Got the cores. Here's about 8-inch concrete thickness inside the building. Here's another 8-inch. It's a structural slab with 8-inch voids. And piers are supposed to be 13 feet deep. That's B3. Boring B4, 8-inch. So consistently we had 8-inch concrete thickness inside. This is a parking lot, B5, 6 inches. 6.5, 7 inches outside B6. B7, almost 6 inches, 5.5 inches. When you do the borings in boring B1 inside, we saw a void about 4 inches thick under the slab. This is the vapor barrier. The yellow stuff is the vapor barrier. See the vapor barrier here? You got 4-inch void under the slab. It's a structural slab system. Here's about 7-inch void. So the soil underneath the slab heaved non-uniform. Some areas it moved 4 inches, some areas moved 1 inch. You can see the 7.5-inch void. That means the soil only moved 0.5 inches. Here's another void here. Is a void in B3. There's a void under the slab, about 7 inches. Void in B4 is a void, is vapor barrier, natural soils. Something about 4 inches, 5 inches void. Here it is, about 5 inches. After we cored, of course, we did the borings. And we use our portable rig system to do the borings, get samples. It's gasoline operated. Measure the water level after we did the borings. We didn't find any water in any of the holes. Then we did exterior borings with our truck mounted rig at 3 locations to a depth of 30 feet. We got soil samples. It was all fat clay. Measured the water level. There was no water in 30 feet below the parking lot. So the water table here is pretty deep. At the finish, we grouted the holes. Got a mixture of bentonite and cement. Mix it together. And they grouted the holes from bottom up to fill the holes. These are in the parking lot. We checked with the probe, make sure the concrete was totally filled. Check with probe, make sure that the grout didn't kind of fall out into the holes. That's the grout. We also installed 2 piezometers, one here and one here inside the building in first floor, 2 piezometers. These piezometers were about 8 feet deep. And we had the screen here. Around it, we put sand. And above that, we had bentonite and had a cover on it. We didn't find any water in any of the piezometers. These are 2-inch diameter PVC pipe. So we drilled a hole, put the PVC pipe in there that was perforated. It has whole holes in it. And put the piezometers in, put sand around it, then put bentonite around it. Put a steel cap on it to measure water levels. You can go back and measure the water levels anytime you want. They did a leak test on this building. There was no leak anywhere. Measured the water levels in the piezometer, and we found no water. B1, B2, dry, dry, dry. We ran micro elevations to define the deflection on the slab based on what the FPA Foundation Performance Association allows. Also, Post-Tensioning Institute. Here you run the micro elevations. You can read what kind of elevation you got. We also did elevations of outside sidewalk to see what the elevations are. And we found out the sidewalk has heaved up at the outside here and get negative drainage towards the building. Yeah, we got a question here. How do you preserve the void below the structural slab when you grout after the coring? You really can't really preserve it. If you grout and fill the holes, I'm sure there's going to be a little mountain of concrete at the area where we did the boring. So that specific area does not have a void in it where you grout. These are the micro elevation data results. So when we look at it, you see the heaving on the sides of the building. This is about 1.8, and here's minus 0.8 here. See the elevations? So these are areas that are heaving on the first floor. So this is the first floor heaving. It's as much as 2.6 inches of heave. It's the second floor heaving. Similar to first floor. Drill footing, exposure, and tests. 2 locations, test pit 1, test pit 3, test pit 2, and test pit 4. We expose the drill piers, evaluate the subsoil conditions, feel out whether or not perch water table exists, measure the depth of piers, elevate the bell and shaft size, identify integrity of drill piers. We also did some test pits to measure the grade beam depth and width and what kind of soils you have in the test pits, and if you have perched water at the test pits. So we jackhammer the sidewalks to get holes in there. We start excavating the soils, try to get to the piers, drill some with the drill, try to remove some of the soils. Drill pier exposure. This was the drill pier right there under the column. This is the bell. Notice the bell is so close to the pier. So they didn't do a good job of making bells. These bells are so close to the piers. Here's another drill pier. Another drill pier. This rod here shows where the tip of the bell is. And again, it's pretty close to the pier. So that means they didn't do much of a bell. That's the edge of the bell right there. Edge of the bell. Here's the drill pier. This is the edge of the bell. This is the drill pier. The edge of the bell is the drill pier. Here's the bell. Here's the shaft. Edge of the bell. So you can tell here where the bell is. Test pit excavation. And test pit number TP3, we found water at the bottom of the grade beam. Remember, there was no groundwater, so there was some water here. We feel like this water that we found is from the gutters. The gutters drained directly on top of the sidewalk. Sidewalk joints were open, so water infiltrated through the sidewalks into the natural soils and got wet. So that's the test pit number 4. Measure the beam depth. Beam is 30 inches. The exterior beam. Measure the width. Trapezoidal carton void edge was 2 inches underneath the grate beams. Here was the void boxes. Underneath the grade beam. Backfilled the whole area where the test pits were and the pier exposure were backfilled with on-site soils. We compacted it. That's what it looked like when it was finished. So drill pier exposure, test pit number 1, all the way down was all fat clay, no water. Pier depth was 10.6 inches. Design depth was 13 feet. Bell size was 36 inches. Design build was 78 inches. Shaft size was 18 inches. Design shaft was 30 inches. So definitely a construction defect here. They didn't build this thing according to the design. The design was 13, 78, 30. They totally missed the mark. So here's the drill pier number 2, test pit number 2. all the way down fat clay. Design depth was 13 feet. The pier was at 10.3 feet. Design depth pier was 60 inches. The bale size was only 36 inches. Design shaft was 24 inches. It was 18 inches. So totally they missed the mark here. Test pit excavation for the basically the grade beams, 0 to 40 inches was all fat clay. And basically the beams were 30 inches and there were 10 inches carton void box in there. So the grade beams matched the design. That's test pit number 4. All the way to 43 inches was all fat clay. The beams, exterior beam thickness was 30 inches. Carton void boxes was there underneath. Water was not encountered. There was no water. And the concrete carton form thickness was 10 inches. And so no water was observed in test pit number 4, but there was water in test pit number 3. Water observed in test pit number 3. Lab tests, we did a bunch of testing, Atterberg limits, string tests, and we developed the soil stratigraphy. Ore1, B1, B2, B3, B4 were done inside the building. We found concrete, a void. Below that, we found a couple of feet of fill. Below that, we saw fat clay, natural soils. The fill was all fat clay too. And outside, below the concrete, we found 30 feet of fat clay, essentially. So somebody asked, does the flooring affect the micro elevations? We correct for flooring thickness and change in the micro elevation when we do the measurement, so it's net elevation. And here's another question here. It says, so fundamental root cause was negative drainage towards the foundation, which was perched under the piers. That was one of the causation. The other causation was construction defect. The piers were not the depth they're supposed to have been. They were not the size that they're supposed to be. Although the depth of it was wrong. There's a design failure here too. 13-foot piers for these fat clays not enough in South Texas. The soils consisted of 0 to 6.8 feet of concrete slab paving. Below that was a void in the floor slab area in the inside. Then we had fill, about up to 3 feet of fill, fat clay. And below that, to 30 feet, we had fat clay. With root fibers to 30 feet. That means your active zone could have been as much as 30 feet on this site. Okay? 30 feet of active zone. The PIs in the fill was 32 to 40. In the natural soils was 39 to 61 PI. Highly expansive soils. Boring logs, looking at boring B1 inside the building. We had concrete slab about 8 inches, void 3.25 inches. Below that, we had fill. Below we had fat clay. Boring B2 inside the building, 8 inches of concrete slab, 7-inch void. Below that, we had almost 3 feet of fill. Fat clay with a PI of 40. And natural soils with a PI of 53 all the way down. B3 inside the building, we have 7 inches of slab, 6 inches of void. Below that, we had fat clay fill. Below that, we had fat clay natural soils with PI of about 30 and 48. And the soil was relatively strong. That's boring B4. We have slab about 7.75 inches, void of about 3.75 inches. Below that, we had fat clay fill with PI of 33. Outside building in the parking lot, we had like 5 inches of concrete, 6 inches of concrete. Below that, we have fat clay all the way down. PIs of course, 40. Really strong soils there. pouring B6 in the parking lot. We had 6.5 inches of concrete. Below that, we had fat clay. But note that we couldn't find any lime in there either under the paving areas. The PI of 41 in the fat clay, 51, all natural soils. B7 outside in the parking lot area, concrete about 5.5 inches. Below that, it was fat clay all the way down. PVR, we calculated the PVR for this site. It came out to be about 3.6 inches. PVR is basically tells you how much heave you can expect at this site based on the soil data that we got. We used text.124e to come up with the PVR calculations. So we had a 3.6 PVR in here, which makes sense because we got 8-inch void boxes. The way you measure the void boxes, of course, is design it is twice the PVR. Engineering analysis. We look at aerial photos. We look at topographic maps. We look at the micro elevation. We looked at perch water tables. We look at the soil moisture profile. We looked at liquidity index. We look at the uplift capacity of these drill piers and look at the depth of the piers. We look at the rainfall data and we look at the GPR results. Here's a site in 1950. It was heavily wooded. That's 2004. No building. 2009. See the building here, 2009, December. 2011. 2016. 2020. 2024. We looked at aerial photo where the building is going to go was flat as a pancake. That's the topographic map. Elevation, we check the elevation based on the FPA as Foundation Performance Association criteria and also PTI, Post Engineering Institute, looking at the guide for performance evaluation of slab on grade foundation as a guideline. Deflection is a change in the basically shape of a foundation after original construction. Deflection is maximum deviation from a straight line between 2 points. Deflection ratio is deflection divided by horizontal distance between which the deflection occurs. So if the slab moves like this is a deflection, not like this. This is wrong. This is your deflection. Tilt for your slab is y over x, which is tilt is the planar rotation, measure the length or width of the foundation system. Allowable tilt is 1% by ASCE, American Society of Civil Engineers, like 6 inches for a 50-foot wide slab. Slope is a small area, basically differential elevation between any 2 points divided by the horizontal distance between them. We use the criteria by FPA and PTI, L over 360. We allow 1 inch of deflection in 30 feet considered allowable. So we ran some cross sections on the first floor, section AA, and section BB on elevations. We plotted the slab elevation. We measured the deflections, L over 1097, L over 1099, 1136. They are smaller than L over 360, so the deflections passes, tilt 0.13%, less than 1%. That's section AA. Section BB, we ran the same way. It's the floor slab deflection. We look at the actual L over 993, L over 1026, L over 1033, less than L over 360. Deflection passes, and the tilt of 0.19%, less than 1%, so it passes. I'm gonna give you the idea what's going on here. So basically the deflection passes and tilt passes. Allowable tilt is 1%. allowable deflection is L over 360, 1 over 30 feet, 1 inch over 30 feet. We look at the perch water, groundwater. We didn't see any groundwater in any of the borings, but we found perch water at boring B3, test pit number 3. We feel like that water is coming in from the gutters dumping on top of sidewalks. Soil moisture, we plotted the moisture in the boring B1 inside the building. And you can see the moisture is not totally dry. This is the dry by TxDOT 124 PVR, and this is the wet by TxDOT. And so it falls between the two. So the moisture is average. B2 moisture is average. B3 boring was the soils were pretty dry. B4 was average moisture. Outside, the moisture was dry. That's boring B5. Boring B6 outside was really dry. B7 outside moisture was kind of average to wet. So we go all over the place on the moisture profiles. We basically plotted a liquidity index for the borings. Liquidity index basically is a review is basically that relates the soil moisture to liquid and plastic limit. So do the liquidity index for the inside the building. We all came out everything above 0. If the moisture liquidity index above 0, that means the soils are not real dry. They're kind of like average moisture. We did the liquidity index. Again, definition of liquidity index is moisture content minus plastic limit divided by liquid limit minus plastic limit. It's basically trying to find out what the moisture content is compared to the soil moisture and the existing moisture content compared to liquid limit and plastic limits. And in the outside, we found the moisture liquidity index kind of close to 0 for boring B6, and then a little bit moist in boring B5 and B7. So outside moistures were generally above dry. It's just kind of a little bit moist. Uplift capacity. We used FPA design criteria for calculation of the uplift capacity of drill piers in expansive soils. If you're a member of Foundation Performance Association, you can get this software for free. Design was piers at 13 feet, but we actually found the piers at 10.6 feet below final finished grade. Okay, so when we run the numbers in this software, you put the soil profile, what kind of soils you have, active zone depth, maximum active zone depth, the column load, but we assume the column load of 116 kips. We put on the piers with the soil data, where the water level is, and based on that, run the numbers, check for uplift loading, and of course, downward movement. And it failed at 10.6 feet depth for piers. So we check the uplift capacity, and again, downward movement capacity. Evaluation of drill footing depths. Again, we checked based on that. We found the pier of 13 feet depth was not enough for this thing to resist uplift capacity to expansive soils. You need to have a pier depth of 25 feet. So we ran the numbers based on 25-foot piers, and it passed. Uplift loading and compressive loading. We looked at rainfall in 2009. The building was started in 2008 or so. We had 28 inches of rain in 2008. 2009, he had 21 inches. 2010, he had 43 inches of rain. So what happened was when they were building this building, it was pretty dry. The next year it was wet. So if any water got in there, it causes expansive soils to start heaving up in 2010. And that's basically what it says in 2009, 2010, and 2008. We looked at the GPR. We did the GPR at 7 locations 4 inside the building and 3 outside. We didn't find any potential voids or moisture under the slab areas or the pavements. These are the GPR scans that was run here. The slab was supposed to be 7.5 inches. Most places was 8 inches. This rebar cover was supposed to be 3/4 of an inch and 12 by 12 inch spacing. When we ran the GPR, it said slab of about 8 inches. The steel cover was 3 inches. The steel location spacing was 12 by 12. So, and here the GPR scan shows no moisture or anything, nothing underneath the floor slabs. Again, this is boring P2. We run the GPR. We measure the concrete slab to 8 inches and the steel spacing of 12 by 12. The steel cover was 6 inches below the top of the concrete. Nothing here on the scan shows moisture or voids. That's basically B3 inside the building. We find slab 8 inches. Average clear cover of the rebar was 6 inches. Rebar spacing 12 by 12. All that meets the project specs of 7.5 inch concrete steel 12 by 12. I don't know, steel cover here doesn't really make sense. It says 6 inches of cover, so it doesn't meet the 3/4 of an inch cover. No moisture or voids under the slab. Here's boring B4 inside, slab 8 inches. The cover was 2.5 inches. Steel spacing 12 by 12. That matches the specifications. No voids or anything in the slab. This is B5 outside in the parking area. It shows concrete of 6 to 7 inches thick. The steel cover was about 1.25 inches. Steel spacing 12 by 12. The specs call for concrete 5 inches, 2.5 inch concrete cover, 12 by 12 steel. Okay. No moisture or anomalies under the concrete. This is B6, 5 inch concrete, 2.5 inch clay cover, clear cover, 12 by 12 steel. What the GPR found was slab thickness of 6 to 7 inches, 1.75 inches cover to 4 inches, steel 12 by 12, no anomalies. B7, same 5 inch, 2.5, 12. This is the boring outside in the parking area. Average concrete GPR said 6 to 7 inches, 1.3/4 of an inch to 4 inch cover of concrete. That means the steel was kind of towards the bottom of the concrete. Steel spacing 12 by 12. No anomalies in there. Was found the GPR within the marked blue area. Reason for foundation distress. So anyway, looking at all this data, we found out the design, the causation for the distress was inadequate design, improper construction, poor foundation maintenance. Foundation, as a result, failure occurred as a result of inadequate geotechnical report. The geotechnical report said put the piers at about 13 feet. Well, actual our calculations based on the FPA document says the pier should have been at 20 feet concerning the depth of active zone and movement active zone on these sites. So the piers were too shallow. It says the pier at basically the geotechnical report says 12 feet. And improper construction. What the specs calls for, the pier is supposed to be 30 by 78 inch bell. Our measurements showed the piers were 10.6 feet deep and they were 18 inch by 36 inches. So they were built not as per the specs. Here's another one. Improper construction. Piers was supposed to be 24 by 60. We measured 18-inch by 36-inch. So definitely a lot smaller than the design. I mean, yeah, the design was 24 by 60. We measured, constructed 18-inch shaft, 36-inch diameter bill. So we feel like the piers as constructed did not meet project specifications. They were smaller and shallower than what it was in the specifications. We'll look at the sidewalks on the building. Some areas that heaved up had negative drainage. The gutters were draining directly on top of the sidewalks. That was not acceptable. Water was getting into the foundation through these joints, causing heave of the columns. So summary, insufficient design depth for the piers. Inappropriate constructed depth and size of the piers. Negative poor drainage. Repair techniques. We came up with a repair based on two options, a cheaper option, a more expensive option. The cheaper option was improve the drainage, fix the sidewalks, and make sure you got 2% slope away from the walls. And then you do chemical injections underneath the sidewalks and the floor slabs inside the building to a depth of 15 feet, and try to get this soil swelling out so that the soil doesn't move anymore. So improve drainage, fix the sidewalks, get underground drainage system for the gutters, and chemical injections to a depth of 15 feet. That's option number one that we should use. Chemical injections basically inject these chemicals like light-grade sulfuric acid into the soil. This is a tank. You put the chemicals in it. This is the clay layer. It's got negative charge. Water here is a positive. The clay wants to absorb the water. You do cation exchange, remove sodium and potassium. You put calcium in it, and the soil does not heave up as much. So the depth should be about, injection should be the depth of the zero movement. This depth is about 15 feet. So if they build a new building, for example, you go out there and do chemical injection. This location should be 15 feet deep. These chemicals go out there and do a cation exchange, and the soil does not heave as much. You run swell test after that to verify that this is the hole for the chemical injection. In the interior, you drill holes and start make the holes in here and do inject the chemicals in there. You go all the way down 15 feet with this rod, and you chemically inject all the way from top to bottom. See, all the way down, it's the chemicals that are going in there. These are the locations of the chemical injection. You do outside too, so that the sidewalks do not move. Level 2. If this system doesn't work, then what we recommended was go out there and improve the drainage, get an underground drainage system for the gutters, and readjust the sidewalks, and then underpin the building and level it using steel pipe piles. These are basically pipes that are screwed together, and you hydraulically push them into the soil. We say it should be at least 25 foot deep for these piles. And some of these piles come with a system that prevents with a collar. These collars goes from 0 to 15 feet that basically isolates the steel pipe pile from the expansive soil. The expansive soils move the collar, but not the pipes. These are steel pipe piles. That's what they look like. They go underneath the grate beams. They screw them together in sections. You hydraulically push it against the foundation system. Use the foundation system as reaction. You can see that here. You push them in. These are the cracks you put in the pipe piles to level the foundation. You can do it in residential and commercial. Uh, when you put these piles in, you have to move their structure all together. So you will have these pipe piles in, and here's the pressure gauges for each location for each pipe piles. You got to control these pressures so that the foundation moves uniformly. Otherwise, you're going to crack the foundation. This is how you put the pipe pile in. So I like steel pipe piles because they got a small surface area, will not be picked up by expansive soils because of the small surface area. They're easy to install inside a tunnel under the structure. They're a little bit more expensive than other methods. Um, if they're pushed to refusal, shallow pipe may move by seasonal moisture. That's why you put collar on them so that they will not move. So if you go 25 foot deep, he won't move. If not pushed to the correct angle, it may lay over. Well, yeah, that's true. Got to make sure it's vertical. The pipe hull can be overloaded, causing the shaft to bend. You got to put plenty of them by a structural engineer. Make sure it doesn't bend. Improper moisture to the pile, poor drainage can cause problems. Now, if they're not, if they're deep enough, they're not going to have any problems, and especially if they have a collar. Structural problems are not conducive to steel pipe piles. For example, insufficient steel in the beam slab are not enough to weight to allow driving the piles. So yeah, if you don't have the reaction, you can't drive them to the proper depth. If the contractor didn't clamp the bucket immediately after driving the piling may spring back. Yeah, you got to make sure you get it all the way down. Drought can cause problems. No, it won't cause problems because if you push it into the right depth and you put collars on it, they're not going to have problems. So a lot of these problems can be mitigated by providing a seal over pipe piles within the movement active zone of 15 feet. Here's some pictures of tunneling that you do under the foundations typically to get access to put these pipe piles in. They are 3.5 or 4 by 4 feet. And you go out there and remove the soils and all that. And you start pushing against the grade beams. This is for press piling pictures. I didn't have steel pipe pile steel pictures. Again, if you got areas where don't have beams, you may have to add a steel beam and jack against it. That's a steel beam. You jack against it. Comments. Despite our recommendations, some movement is going to occur. We recommend after any kind of the foundation repair, wait 6 months and go back and remove and replace the bad cracked CMU blocks and the bricks. Make sure there's no leak with the plumbing test. A structural engineer need to be involved with design of the foundation system for repairs. So basically, again, we have a case over here that the geotechnical report was wrong. The contractor didn't put the right size piers and the right depth and caused foundation problem for a very expensive school. This is a big problem. So original design, change order, foundation repair, costs a lot of money. If you got pictures of projects, send it to me.